So we're building our own battery cells. We think the most advanced cell in the world here at Giga Texas.
Tesla has quietly revealed a battery that could end the lithium era and change the future of electric cars. Inside Giga Texas, a new design emerged without a launch event or press conference, yet the numbers are staggering. It can fully recharge in 5 minutes, deliver more power the hotter it runs, and last for hundreds of thousands of cycles without fading. For more than a decade, lithium defined the industry, but Tesla has stepped away from it. With this breakthrough, they are not competing in the old race, they are starting an entirely new one. The lithium's era and its limits, lithium-ion batteries created the modern electric vehicle industry. From the earliest Tesla sedans to the compact city cars of rival brands, lithium cells became the default power source. They were compact, reasonably efficient, and light enough to make electric transport practical. For a time, they were celebrated as the technology that finally allowed the automobile to break away from oil. Yet, inside laboratories and design studios, the story was different. Engineers understood that lithium was not perfect. It charged slowly. It lost capacity with every cycle, and under stress, it could overheat with dangerous results. The industry lived with these weaknesses because there was no viable alternative. Every year brought incremental changes that seemed to promise more than they delivered. Slightly improved charging networks shaved minutes from wait times. New cell geometries squeezed out a few extra miles of range, and advanced cooling systems managed the heat a little more effectively. Progress was real, but it was never transformative. Drivers still found themselves waiting at chargers longer than they wished, and every battery pack still carried the risk of thermal runaway if temperatures climbed too high. Even as headlines celebrated breakthroughs, the underlying chemistry had not changed. Lithium remained limited by physics, and those limits defined the experience of every electric car on the road. Lithium also carried problems far beyond the engineering lab. Global supply chains were fragile, and prices swung with political tension and mining bottlenecks. Cobalt, used in many lithium cells, was often extracted under conditions that sparked international criticism, and the cost of scaling production mounted year after year. Automakers were locked into a material that was expensive, environmentally taxing, and vulnerable to forces they could not control. What had once looked like the clear solution began to resemble a ceiling on the industry's future. For Tesla, this was not acceptable. The company's mission was never simply to build electric cars, but to accelerate the transition to sustainable energy. To achieve that, batteries needed to become faster, safer, and cheaper, not in small steps, but in leaps. While the rest of the industry worked on squeezing the last ounces of performance out of lithium, Tesla's engineers in Austin turned their attention to a different path. They asked a question few others dared to ask. Why keep refining a material that had already reached its peak when another element could offer an escape from every limitation at once? The Austin breakthrough. Inside Giga Texas, Tesla's engineers began to challenge the assumption that lithium was the only viable chemistry for electric cars. For decades, researchers had experimented with aluminum, a metal that was cheap, abundant, and remarkably conductive. On paper, it seemed like the perfect candidate. In practice, it always failed. Aluminum ions could store energy, but they suffered from ion lock, a problem where they became trapped and could not release their charge quickly enough for real-world applications. In laboratory after laboratory, aluminum batteries either degraded too fast, overheated uncontrollably, or failed to deliver usable power. Most researchers abandoned it, treating aluminum as a dead end in energy storage. Tesla refused to accept that verdict. In a sealed lab within Giga Texas, a small team revisited the problem with tools that earlier generations of engineers did not have. They experimented with substrates built from carbon graphene structures layered at atomic scale. By embedding induction points directly into the lattice, they created pathways that allowed aluminum ions to move freely rather than becoming trapped. The structure not only solved the ion lock problem, but also exploited aluminum's natural conductivity, enabling charges to travel with extraordinary speed. The moment it worked, everything changed. What emerged was not just an alternative to lithium, but a complete reset of the rules. The new cell architecture allowed energy to flow without fade, without lag, and without the runaway heat that had haunted lithium designs for decades. Unlike lithium cells, which degraded as they aged, the aluminum system stabilized under stress. It grew stronger as cycles accumulated, with the internal structure realigning itself after every discharge. The result was a cell that promised near infinite life, capable of delivering full capacity even after hundreds of thousands of cycles. Tesla called the next innovation quantum burst control, or QBC. Traditional batteries released energy in a steady stream limited by internal resistance. QBC reshaped that release into high-speed pulses, timed with extraordinary precision. The effect was immediate. Instead of waiting for the car's systems to draw power, the battery delivered it almost before the driver pressed the accelerator. Torque arrived instantly with no lag, creating a driving experience unlike any lithium-based system could achieve. The numbers recorded in testing stunned even Tesla's most optimistic engineers. The aluminum ion cell produced over 7,000 watts per kilogram, more than 5 times the output of Tesla's existing 4680 lithium-ion design. The performance did not collapse under heat. In fact, it improved. Lithium batteries typically risk thermal runaway past 40 degrees Celsius, requiring elaborate cooling to stay safe. The aluminum ion cells operated at their best at 85 degrees Celsius, delivering stable power without strain. What had once been a fatal flaw in aluminum chemistry became its greatest strength. In extreme heat, on racetracks, or under heavy towing loads, the battery's performance climbed rather than declined. The implications of such a discovery extended far beyond faster acceleration. If a battery could charge and discharge at those rates without degrading, then charging times themselves could collapse from hours to minutes. In a closed-door demonstration, Tesla engineers connected a prototype vehicle to a standard supercharger. Within 5 minutes, the pack had reached 80% capacity. Observers described the scene as surreal. There were no roaring fans, no stressed coolant lines, just raw energy transfer at a pace that had once been dismissed as impossible. This was the moment when the argument against electric cars changed forever. For years, skeptics had pointed to long charging times as the reason EVs could never replace gasoline. That excuse evaporated in 5 minutes inside a Tesla testing bay. The aluminum-ion battery had not only matched the convenience of refueling, but surpassed it by combining speed with longevity and stability. Perhaps most remarkable was the resilience of the chemistry itself. In testing, cells were cycled 500,000 times without measurable capacity loss. Traditional lithium batteries began degrading after a few thousand cycles, gradually losing range until replacement became inevitable. Tesla's aluminum-ion cells not only resisted this decline, but showed signs of strengthening as the internal lattice restructured itself under repeated stress. The analogy engineers used was bone healing stronger after a fracture. Instead of dying with use, the battery improved. The breakthrough in Austin was more than a scientific achievement. It was a strategic weapon. Lithium was scarce, expensive, and tightly bound to global supply chains. Aluminum was abundant, cheap, and available in nearly every industrial economy. By shifting chemistry, Tesla escaped the bottlenecks that limited competitors. It no longer needed to fight for lithium reserves or navigate the geopolitical friction that came with them. With aluminum, the supply chain problems that once threatened EV growth simply disappeared. What began as an experiment in a single lab quickly grew into Tesla's boldest plan yet. The company realized they were not simply improving batteries, but eliminating the foundation on which the rest of the industry still depended. While competitors worked to improve lithium packs by a few percent each year, Tesla was preparing to release a product that redefined performance, cost, and longevity in a single stroke. The Austin breakthrough was not another step forward in the lithium era. It was the first chapter of the post-lithium world. If Tesla had finally built a battery that outperformed lithium in every way, what kind of machine would they create to prove it? The Model 2 and the scale of a revolution. Tesla's answer came in the form of a project codenamed Redwood. Rather than slot the new aluminum-ion battery into an existing vehicle, the company designed an entirely new car around it. Internally, it became known as the Model 2, a compact electric vehicle intended not as a luxury showpiece, but as a mass-market disruptor. For years, Elon Musk had spoken about a truly affordable EV that could match or surpass the capabilities of gasoline cars. With the aluminum-ion breakthrough, that vision was no longer speculation. It was an engineering reality. The specifications sounded more like science fiction than product planning. Engineers promised a base price under $16,000, a range of 550 miles on a single charge, and a recharge time of 5 minutes. Industry veterans dismissed the numbers at first, pointing out that even the most advanced lithium cells could not reach such performance without astronomical costs. Yet Tesla was no longer working within lithium's limitations. The aluminum-ion chemistry delivered energy density and charge rates that rewrote the mathematics of electric vehicles. For the first time, an EV could cost less than a gasoline equivalent, travel farther on a single charge, and refuel in less time than it took to fill a tank. Prototypes were tested under plain black wraps, disguised to look like unfinished shells. On private tracks around Austin and later in California, the Model 2 accelerated with a violence that startled journalists invited for secret ride-alongs. 0 to 60 came in just over 3 seconds, and unlike traditional EVs, the performance never faded. Lap after lap, the car delivered the same explosive torque without overheating or throttling. Test drivers noted the absence of cooling fans struggling to keep temperatures down, the absence of warning messages asking for a cool-down, and the absence of the sluggish response that crept into lithium packs under stress. The car simply kept going. This consistency was not only about performance thrills, it was the key to changing perceptions. Electric cars had long carried the stigma of being fragile under strain, with drivers told to temper their acceleration or limit their charging habits to preserve battery life. The Model 2 shattered that caution. It encouraged drivers to push harder, tow heavier loads, or drive in extreme climates, all without fear of degradation. In desert heat, on mountain passes, and during repeated launches, the aluminum-ion battery thrived. Its internal structure grew stronger under pressure, creating a vehicle that seemed almost indestructible. Building such a machine required production on a scale no conventional factory could provide. That challenge led to the creation of Giga Mexico, Tesla's first plant dedicated to aluminum-ion batteries. Unlike lithium facilities, which relied on water-intensive coating processes, Giga Mexico employed a dry electrode method that cut production time in half and eliminated billions of gallons of water waste each year. From raw aluminum to finished packs, the process took less than 72 hours. The factory was designed not only for speed, but for replication. Tesla envisioned a swarm of smaller autonomous micro-factories scattered around the world, each capable of producing up to 1 million battery packs annually. By decentralizing production, Tesla sidestepped the geopolitical choke points of lithium and positioned itself to scale faster than any competitor. The shift in manufacturing strategy was as radical as the chemistry itself. Traditional automakers were still grappling with the logistics of lithium supply when Tesla was already building a global network of aluminum-ion micro-factories. Each site could operate semi-independently, responding to regional demand and insulating Tesla from political shocks. It was not just a manufacturing plan, it was an energy independence strategy, one that promised to reshape both transportation and geopolitics. Yet, for all the talk of chemistry and factories, the most compelling proof remained the driving experience. The Model 2's torque felt instantaneous, not as a surge, but as a seamless flow of power that connected driver and machine. Tesla's AI-driven power management system adjusted delivery in real time, anticipating changes in road grade, driving style, and even traffic conditions. The result was a car that felt less like a machine being commanded and more like a partner responding in perfect harmony. Every press of the accelerator was met with exactly the right response, whether that meant a gentle glide through city streets or a hard launch on a freeway on-ramp. The combination of affordability, range, speed, and charging convenience set a new standard for what drivers expected from an electric vehicle. It was no longer a matter of asking whether EVs could compete with gasoline cars. The Model 2 demonstrated that EVs could outperform them in every dimension that mattered. With a price tag within reach of the global middle class and a charging time measured in minutes, Tesla was no longer just leading the EV market, it was redefining it entirely. If Tesla has already built a car that makes lithium obsolete, what does this mean for the rest of the industry still locked to the old chemistry? The end of the lithium era. The unveiling of Tesla's aluminum-ion battery did not just raise eyebrows in the automotive world, it forced the entire energy sector to confront the reality that lithium's time at the center of innovation was running out. For more than a decade, automakers, governments, and investors poured resources into lithium supply chains, convinced that it would remain the standard for decades to come. Now, that assumption was shaken. The aluminum-ion battery demonstrated performance numbers that no lithium system could match, and more importantly, it delivered those results at a cost and scale that made mass adoption feasible. The industry could no longer ask whether lithium would eventually be replaced. The only question left was how quickly the transition would unfold. Competitors reacted with a mixture of skepticism and urgency. Some executives dismissed Tesla's claims as exaggerations, while others scrambled to secure research partnerships to avoid being left behind. In Europe, energy regulators began commissioning reports on how an aluminum-based supply chain could be integrated into the continent's manufacturing base. Japan, already preparing for the 2030 World Expo, accelerated plans to test autonomous production facilities designed to mimic Tesla's Gigafactory model. Even in the United States, where policy debates often slowed technological adoption, the Department of Energy began quietly funding exploratory projects into post-lithium chemistries. No nation wanted to wake up to a future where Tesla controlled not only the best cars, but also the most advanced energy storage systems on the planet. The implications stretched far beyond vehicles. Lithium batteries were not only powering cars but also stabilizing grids, backing up data centers, and storing solar and wind energy for homes and industries. By moving to aluminum, Tesla broke open possibilities across every sector that relied on stored power. A battery that could charge in minutes, deliver energy in precise bursts, and endure hundreds of thousands of cycles without degradation promised to transform renewable energy infrastructure. Solar farms could store daylight energy with virtually no loss. Wind installations could balance output with unmatched stability. Homeowners could install packs that outlasted their roofs, never needing replacement. Entire cities could operate with backup storage that functioned for generations rather than years. The geopolitical consequences were just as profound. Lithium reserves were concentrated in regions such as South America's Lithium Triangle and parts of Africa and Asia. Control over these reserves created new strategic rivalries and trade vulnerabilities. Aluminum was different. It was the third most abundant element in Earth's crust, mined and refined in dozens of countries across every continent. By basing its technology on aluminum, Tesla freed itself from the resource bottlenecks that had slowed the growth of rivals. The company's plan for a swarm of decentralized micro-factories only amplified this advantage. By producing batteries locally with abundant material, Tesla sidestepped the political and logistical risks that had defined the lithium era. Critics warned that job displacement would follow, both in mining and in traditional automotive supply chains. Yet Tesla argued that the shift would create new industries as old ones waned, building and maintaining micro-factories, refining the advanced substrates needed for the new cells, and designing vehicles to exploit the chemistry would demand an entire ecosystem of skilled labor. Instead of a few choke points where lithium was extracted, the aluminum era promised a distributed global network of production and innovation. For consumers, the changes would be immediate and dramatic. Electric vehicles that once cost more than their gasoline counterparts could now be offered at prices affordable to middle-class families worldwide. Range anxiety would disappear as 500 miles became standard and charging took no longer than a coffee stop. Longevity concerns would vanish as packs outlived the cars themselves. Even the second-hand market would be transformed, with used EVs retaining full battery performance decades after their original sale. In the history of automobiles, no single innovation had ever collapsed so many barriers at once. The deeper story, however, lay in what this meant for the idea of energy itself. If storage was no longer fragile, expensive, or slow, then renewable generation could finally expand without limits. The old argument that the sun does not always shine and the wind does not always blow lost its bite when batteries could hold massive reserves for as long as needed. What began as a breakthrough in a car company's lab became a cornerstone for reimagining how societies power their industries, their homes, and their cities. Tesla's aluminum-ion battery was not a small step beyond lithium. It was a leap that marked the end of an era. Where lithium represented compromise and constraint, aluminum represented abundance and freedom. The industry that once fought to stretch a flawed chemistry now faced a future defined by a material that had been overlooked for decades. The lithium age had delivered progress, but with limits that were always visible. The aluminum age promised to erase those limits entirely. Tesla's aluminum-ion battery signals the end of lithium's reign and the start of a new energy era. And while the rest of the industry scrambles to adapt, Tesla is already years ahead. If you want to stay updated on every breakthrough shaping this revolution, make sure to subscribe, because the next chapter in this story is coming fast.